BF theory. And this is a topological field theory with a Zn times a Zn global symmetry, gauge symmetry. And also a Zn times Zn global symmetry. Okay. And the what type of the rank of the symmetry we will see is going to depend on what I can construct. So in the first lecture, we'll try to review or study this example. So just to get a calibration sense how fast I can go for the mathematicians in the room who have heard of this model, who knows what it does. Okay, it will not be then a total waste of time. And for the physicists in the room, okay, you should more or less understand quite a bit about this theory. So hopefully I might say something that you may not have known. But it is a model that if you're a mathematician and want to have a canonical model in your head of how physicists try to think about some of these structures, this is a good example to work through. And we'll try to do two levels so we can see what we get. So we already argued from last time how when you write down Lagrangians, you can have couplings that are non-topological and couplings that are topological. So today we will just start with a theory. I will just express the partition function. It's an integral on two fields, which I'll call B C, and the yi integral times, I'm integrating on some manifold M of D dimensions, okay? And then I have a pair of fields B with a coupling of the following, where I have B wedge DC. This is so I can pick the degree of B to be, let's say, some P form. Then C is going to be D minus P minus 1. Okay, so it's a first order action. And then I have an integer n here that labels the theory. So I have n, and then I have b and c, and this is a simple theory that we want to study. And you can see from our previous discussion, there's no metric dependence. So this is a topological field theory. And this topological field theory, while it seems benign, is quite interesting and have a lot of fun structure. Okay. So for most of the talk, I might keep it a bit simple where I will fix, it's important to fix the dimension to just keep track of things. We'll fix D equal to 5, where in that case, we have two forms, a B, which is a 2 form, and a C, which is also a 2 form. And I will not worry about the label. But everything we will see will generalize in any dimension and for any pair of these two guys. Okay, so that's one data, and n is going to be always an integer. So the next thing that I want to tell you, that I should tell you at this level, is certainly when we write down an action like that in physics, we expect B to have a gauge symmetry, at least a local gauge symmetry, where B shifted to B plus from globally defined one form. This is the symmetry of this problem, and also C shifted to C plus D of some lambda 2. Call it lambda 2 and lambda 1. So this action have this local symmetry, which exists. Okay. The next thing that you want to pick, typically when I give you a quantum field theory, this has a local symmetry, but I need to pick some global structure associated to it. We have various choices that we can pick, and each choice have very different implications. One, we could say that the gauge group for B and C is R. We have R gauge symmetry. What that means is that all gauge identifications are just that, where lambda1 and lambda2 are globally defined in the story. You could have a choice where we say that B or C has the transformation B plus omega, where omega is an element of H2, H2 with Z coefficients. Okay. You also have a third choice, which is for B going to B plus some omega, or omega here is some element of H2 with coefficients, let's say in R. Right. So any closed. So each one of these choices have different implication of the field theory, right? So typically this is the one we call a U1 gauge symmetry. This is a U1 gauge symmetry to keep in mind. And the reason why it's important to think about this is if I have these fields with a gauge transformation of this kind, I can ask what are the
like in the second one.
Good. We'll come back to something like that. But here I just say that omega is identified with H2 and Z. There are the torsion elements. I don't need to say much about this. Okay, so the question you might ask here is, what are the observables of this quantum field theory? Go ahead.
In the third case, so the first is R gauge symmetry, the second one, and the third?
The third is actually is going to be trivial. We'll see in a moment.
These options, do you do it only for B and C stays R gauge?
I can do it both for B and C, so I have in principle extra. And every single time, what the theory is actually could be dramatically different. And the way we want you want to see that is you want to think about the observables of these theories. Go ahead.
Yeah, I was just are these choices you make for your theory? So
yes,
you always have those like B plus D lambda gauges, and then you say, okay, we add extra gauge symmetry to it.
So right, so you have the local gauge transformation, right? Because in physics we have local gauge transformation, and in fact that's where we always start. And then you have to pick some global structure, your gauge field. So these are different choices of global structure that I can impose on my gauge field. And the thing that to highlight is the different global choices of global structure will have different implication of what the theory is. So the observables of the theory, meaning what are the gauge invariant operators, coming from the fact that I have that local transformation, I can write observables which are going to be take value on some two-dimensional closed submanifold. I'll say WC and WB. Right as the holonomy 2 pi I integral on gamma times C times the gauge field C, then exponential 2 pi I integral gamma prime of B. Okay, so these observables, as you can see, under the local gauge transformations, these are gauge invariant operators. Okay, but now we can look at these different choices. Okay, under these different choices here, for example, if we pick the R gauge transformation, these are gauge invariant for any choices of C, for any choices of globally defined B and C. Right, so any field these are gauge invariant. So the first one, we have fields operators are gauge invariant. for all choices of B and C. So these are always good operators. And then the next one is 2. Because we have this gauge transformation that B shifted with something valued in H2 with Z coefficients, that also gives me gauge invariant operators, because if I shift with something that is in integral cohomology, I get 1. I get some integer, and then that shift is just at 1, right? So for here, we see that we have compact gauge group which correspond to B and C both being in U1. So this second identification identified, and in particular, when we say B and C is in U1, what we mean is that the holonomies are valued in U1, and the actual B, the ones that can contribute here, actually, I don't want to say this yet. We'll leave this point for later. And then lastly, if we look at the 3 case, because I can shift the gauge field for any choice of a closed form, what that means is that if I have any value to this integral that's non-trivial, then I can pick a class to cancel it. Okay? So in the 3rd case, the theory is trivial. And there are no gauge invariant observables.
These are all observable.
So this is a unit thing that I can construct as gauge invariant under that. So any other observable that I can construct have to be a function of this object. If this object is trivial, then all other functions that I can construct would be trivial.
Don't you have like some sort of
Good. So there's a duality here where one is like the tooth for the other. You can independently define tooth, but later we'll see that we don't have to worry about that. So the point here is that, you know, typically in physics, we would say that you pick a local gauge symmetry, but the global structure that you put in is important, and you have to tell me what it is, and that will determine the physics. So for the purpose of this thing, we will now discuss these classes of systems, and we'll try to analyze this theory where we pick both B and C to be U1 gauge fields. Okay, and then we'll find, even with that choice, the actual observables live in a smaller gauge group, and it will be a discrete gauge group. Okay.
What is the difference between the observables in the case 1 and case 2?
So the difference here is literally that these gauge fields are in R, whereas in the second one, the gauge fields are compact, are in U1. There is an identification. So yeah, so any choices of C that I can pick here, I get a good observable for any gamma.
Like the fact that the observable is like the exponential of 2 pi I does not project the R to U1?
No, it does not. It doesn't. In particular, it becomes a question of what choices of gamma are you having in. Okay. So the choices of gamma that you can have could be different. Go ahead.
And so do choices of like gauge of gauge involve?
Gauge of gauge, what do you mean?
Like we can do like gauge transformations of the gauge transformations. Does that not impact the list of observables? Like we just have to choose this level?
That might be an issue if you have other gauge fields that care about it. So this is just these 2 fields. So maybe I don't quite understand the question. So what are you asking, that I shift lambda?
Yeah, like lambda admits a gauge transformation too.
But lambda itself is a gauge parameter. What you're asking is that, can it be that I have A and then I have another field where the shift of lambda, where lambda becomes a shift symmetry for that field. And then something like a Stuckelberg field.
Yeah, and so like the choice of that doesn't affect, like
Good.
this presumably doesn't affect the list of observables.
Good. So that in this theory, it doesn't, right? So let me maybe clarify the question for everyone else. The question he's asking is that suppose, so here we have, let's say C, which have some gauge transformation, C plus D of lambda. You could have, let's say, another field in my theory, let's call it phi, such that the shift, this gauge transformation will also have a shift for phi, which acts on phi with as a shift symmetry. Right? So you could have an extra field where this gauge transformation is shift symmetry for that. And then I could treat phi as a gauge field. And then treating phi as a gauge field, phi also has some gauge transformation, so D of lambda twiddle. So this would seem to say that the gauge transformation of this has another gauge transformation. In cases when you have something like this occur, I think we'll encounter this later. This is a case where actually this field is not itself dynamical because it's a pure gauge field. And whenever I write gauge invariant combination, it will be a field which I can remove by a gauge transformation of C, okay? Unless I suppose I add a boundary to the theory, then that becomes dramatic, or I add other operators. So you can have operators that can distinguish whether this phenomena occurs or not, and we'll encounter cases of that. But for now, we will do just the simplest thing, where you just have these two fields. There is nothing else around that can sort of that could be related. Any questions? Any questions? Okay, so we want to analyze this theory and see when are these observables non-trivial. Okay. Okay, so the thing that I might want to compute is the correlation functions of these two operators. I want to say, what is WC of gamma prime times WB of gamma? I want to compute this observable. So we can compute this by just plugging both of these in the action in the path integral. Have an integral of E of B, E of C, exponential of F, the action, plus by I integral of gamma C. So here, when I say I insert this operator, what I really mean is I compute this quantity here, e to the minus is times WB of gamma inserted with WB of gamma prime. Two different gammas, right? But as I said in the previous lecture, that when I'm computing things in the path integral, the operator that I insert them as C numbers. So I can freely add the things in the exponent, okay? So in general, of course, that's not true. If these are operators, I have to worry about commutation rule. But when we evaluate the path integral, these are C numbers, so we can always put them in this way. So this object on top is easy to evaluate. We can evaluate it by simply observing that I can shift, let's say, C to C plus some C0 here, okay, with the constraint, right, with the constraint that D of C0 is going to be 2 pi I over N or times n times the delta function on gamma. Okay. Then the evaluation here is minus I. We have an integral of question of B wedge B of C plus B by n 0 here. Want this to be B prime here. So this evaluates to, and I have another term here, which is C plus C0, which I cannot forget. This shift does nothing for me, right? Because in the first term, I get 2 pi I n times integral of B wedge B of C. I can shift the path integral measure without a problem. Let me finish and then come back. And then this choice of a shift with in terms of a flat connection will cancel this B term at the level of the action. So this becomes an integral of gamma of C plus, take this out, the integral times an exponential of 2 pi I over n times integral of gamma of C naught over here. So here I have then this quantity here, this path integral over B. And then here I can also just shift what I mean by B to absorb this term gamma by a flat connection. So this term is simply going to equal to my original path integral that I had before, multiplied by this phase, 2 pi I over n times this integral here. So C0 is delta function localized on gamma prime, and you can argue that this is just the linking number of gamma with gamma prime. Okay, there was a question there.
Yes, so if B and C are two forms, then gamma is a surface.
Yes. Okay. So what we conclude from this analysis is that the correlation functions WC of gamma, WB gamma prime, is the value of the original partition function, which is something that we can always normalize, times an exponential of 2 pi I over n times this linking number of gamma times gamma prime. Go ahead.
You said that you can get rid of this integral over gamma C by another shift. Shouldn't this also give you a contribution then?
Good. It doesn't give me another contribution because if I shift B to absorb this, it cannot give me another contribution because this extra contribution here was coming from that I shifted C first to get rid of this term, but then I have the holonomy of C present. So because of the holonomy of C is present, that's how I got this term B there. Right.
What is uppercase N?
Uppercase what?
N.
Good. So uppercase N is an integer parameter, which is part of the definition of the theory.
Oh, sorry.
Okay. It's an important number that's going to play a role here. Right?
There is a misplaced bracket you have.
Do I? I probably
C0 should also be multiplied by B
where
in the middle line.
here.
Yeah, to the right, left.
Is that your worry?
Yeah.
Okay, good. So this correlation function is non-trivial, right? It's giving us a value. But then we can now play with this and try to understand some properties of it. Suppose now I take gamma and I shift gamma by n times some other curve phi. Let me not call it phi. Let me call it beta.
What is L of gamma prime?
Oh, this is a linking number. This is the link of gamma with gamma prime.
And also to cancel C, you generate a boundary term. Because you need to integrate that.
Yes, but I'm doing this in a space without boundary, so it's fine. Go ahead.
Sorry, you're taking the linking number of two surfaces in R5? That's,
In 5 dimensions.
okay, that's just a thing you can do.
If the dimension of the surfaces add up to the dimension of the space minus 1, it is a non-trivial link. So if I shift gamma by gamma plus n beta, right, then the link is going to shift the link is going to shift to the original link number of gamma times gamma prime times n link of beta with gamma prime. So under this transformation, the link will shift with giving you a link of beta plus gamma prime with a value of n. So this cancels and becomes 1. Similarly, if I do it for gamma prime, I get the same property. So we observe from this thing that WC of gamma identifies with WC of gamma plus n times another closed curve. Similarly, WC of WB of gamma prime will identify with WB gamma prime plus n times beta. Or said another way, if I just pick gamma to be n times some other curve, I conclude that WC of gamma raised to the n power is an identity operator, and WB raised to the n power of gamma prime is also the identity operator. So what this tells me is that these holonomies, although I started with holonomies that were valued in U1, the non-trivial ones that survive are the ones that are valued in Vn, the Vn group.
There's a Z mod n group of operators.
So I have these operators which are in U1, right? But for each one of these operators, I've raised them to the nth power, they become an identity, right? So there's a Z mod n. It's only the Z mod n elements that are non-trivial.
Exactly, but there's many curves. That's good.
Yes, yes. So this statement can be summarized in the following way, which is that if we consider the sequence of Z mod n into a U1, then n times the U1 going to 0, there's a long sequence of cohomology groups here, right? Where I have H1 with coefficient in Vn that goes to H1 with coefficients in U1, which goes to H1 with coefficients also in U1, and then it wraps around. And this map here, what it's saying, I take the element here of A, and this goes to the element here of A to the n. So this element of A to the n is trivial, so I can lift A into a Zn. So even though I started with a gauge theory, which has a U1 times the U1 gauge group, what we observe actually in the gauge theory, the gauge symmetry is smaller. It's much smaller than a U1 squared. The gauge theory is a Zn times a Zn symmetry. questions? Go ahead.
So in the beginning, when you had written down, this theory has a Zn cross Zn gauge global symmetry, you were talking about this one form, this symmetry.
So let me get to the global symmetry, right? So in this construction, we started with a U1 times U1, and then we observed that when you study the actual observables, the observables tells you that you have a smaller gauge group, which is a Zn times Zn, not a U1. So since this is now a topological TQFT, it doesn't depend on the metric. You can compute the Hamiltonian, and the Hamiltonian is 0. The elements here, I can understand this commutation, this correlation function more specifically in the following way. Let me see, where can I erase? Right here. Oh, good. Okay, so this statement here, what it really translates to, so I'll make a statement without proof, but I can prove it later if you have to. The WC acting on WB on gamma prime as non-trivial operators gives you exponential times the linking number 2 pi I over n times the link of gamma prime times the commutator WB of gamma prime times WC of gamma. Okay, so this is an action which tells you that if I try to, I read this in the following way, that if I take WB as the operator of the theory and I act with WC on this, I get a charge over here times WB. Okay, so this is a group action. And I could also read it the other way around. So from this perspective, what it tells you is that WC, the operator of WC is a topological operator that generates a Zn global symmetry where the charged object is RW, the curves, are the curves WB of gamma. Okay, so this is a group element, it's a Zn group that's acting on some charged objects, which are these guys. So that's one global symmetry that this theory admits. And then if I read it the other way around also, then I could see that WB also is a group element that acts on WC, which are the charged objects. So you get so this is a theory which is a Zn times Zn gauge group, but also it's a theory that admits a Zn times Zn global symmetry.
What about WC acting on WC?
They commute. Okay. So this statement here, you could ask, how do I show that this statement is true? So here we computed the correlation functions and saw that you get a phase, which is a link, and then this phase is the charge under the group action over there. A question you could ask is, how do I actually see that these operators satisfy that condition? To see that, I have to study the quantization of this theory. Because this, to see this, I need to think about this theory as a quantum theory, not as a classical theory. And the point is that if I look at this partition function over here, and I think about it at the classical level, where this is the action of my theory, the theory seems trivial classically, right? Because if I compute the equation of motion equation of motion for my system, let's say for B is going to tell you that n dc is equal to 0. And if I look at the equation of motion for C, I find that n dB is equal to 0. So classically, this theory seems trivial, right? Because classically, if I look at the equation of motion, I just see that I get flat connections. Doesn't seem to be dynamical. So is this structure that we observe here, where we see that at the level of the quantum theory, that I have something actually interesting, you see, it has to follow because the theory has to be quantized. Okay. So the quantization of this theory, you can study it in various ways. We can typically, one way I can study the quantization of any Lagrangian theory is by just doing a Hamiltonian quantization. I will make a statement. If you don't know what it means, ask and I'll try to clarify. Otherwise, we can try to talk about it off shell, outside. Off shell. We are always on shell. We are never off shell. I think about quantum mechanics too much. Okay, good. So the action for my system is 2 pi I n times B wedge dc. So under Hamiltonian quantization, I can think about this theory, and I can look, if I take B as my variables of my system, they're the canonical momentum conjugate to it, right? The momentum conjugate to B is, from here, is just going to be n times C. Similarly, if I take C as my variable, its momentum conjugate is n times B. So in quantum mechanics, when you have two variables that are conjugate to each other, then we have the Dirac quantization condition where we say B commutator with C is 2 pi I. So let me write this formula first. We have the famous relation in the quantization that if I have a variable and I look at its conjugation, its commutator with its momentum conjugate, I get 2 pi times I times h bar. If I have, write it, the 2 pi is there. Right, so this is what we mean by quantization in the simplest case. So if I look at the quantization for here, I have B times C is going to be 2 pi I. So we set h bar to 1 over n. Then there's a delta function associated to the value of x, y of these two, x minus y, times a volume of some four-dimensional space where they live. So this is the canonical quantization condition that we have for these fields B and C. And from this canonical quantization condition, now you observe why we have this non-trivial group action here. Because what it tells you now, if I have the exponential of 2 pi I B on some gamma times the exponential 2 pi I gamma prime of C. So this is going to be the same as the exponential of the commutator of 2 pi I integral of gamma of B, integral of gamma prime of C, times the switching the two. There might be a minus sign there. B. So this phase factor that appears here from the commutation of these two guys following this delta function here is what picks up exactly the link number that we have down there. So as a classical theory, the theory is trivial, but as a quantum theory, it corresponds to a non-trivial Zn times Zn gauge group with non-trivial operators with a Zn times Zn global symmetry.
Usually when we do quantization, we kind of fix in a space
Yes.
surface.
Good.
In this case, like, are the gammas space like
So good. So so this is. I was hoping somebody would ask. This is why you have that guy here, right? So our space X in 5D is split into M times R, where R is time. Right? So this commutation rule is taken in M. But then once I have this general commutation rule, I can take gamma and gamma prime into 5D, right? And then I can consider the embedding of gamma and gamma to be any configuration that lives there. So this computation here, this is this integral here. I can pull them out, so I get a BB, and I get that delta function. Then you indeed recover the link number. It's a computation to do, but you can do it and let it check. But the statement that you're saying is that when I write this commutation rule, I have this volume factor that I shouldn't forget, right? And that's related to that I have to pick a time, right? And then these B's and C's are going to be B that live along the spatial section. Right. That's correct. Any more questions?
Could I just ask what you exactly mean by this is a Z-mod N gauge theory? So you first constructed it as a U1 gauge theory, and then a posteriori you realized like I could also take C and B to be Z-mod N valued. Is that what you're saying?
So I constructed this to be a U1 times U1, right? But then I at the end of the day, I see that when I analyze this theory, only the gauge fields that are in U1, that are in Zn times Zn are the ones that survive, right? So all other ones are projected out, right? So this is why, so I said this rather fast, over here, right? So I started out with a U1 gauge group here. But then I find that the non-trivial gauge fields always in the list through the end. So I have a genuine Zn gauge group. Okay. And maybe I have time. Do I have time to take it? And okay, so the reason why I've been doing this because when I think about what the U1 gauge group is, it's much more non-trivial than what we just think about. So U1 gauge group is given by some differential cohomology, right? So maybe I can just take a parenthetical things and just say that. That might explain your question better. So to answer this question, I need to briefly, I guess, remind what is the data of a U1 gauge group. This is a non-trivial thing. So in physics, also properly in mathematics, when we say that I have some gauge theory A, which is a U1 gauge group, which have a gauge identification of this kind, where this is valued in H. Let's call this some P-form gauge group, HP of H mod Z. If this is my gauge identification, you could ask, what are the independent gauge field configurations, right? And when you ask this question, you find that the answer is a lot more non-trivial than you might expect. And because of that, you're allowed to have these smaller things embedded inside of it. So the way you try to characterize the independent gauge groups is by looking at this Shiga-Simons map, gamma, which will act on some closed curves, sigma p, which has exactly what we call the holonomy integral on sigma p of A. And then what you would like to do is characterize all non-trivial elements of gamma here. So this is going to be characterized for you by some H check differential cohomology, which we write typically as H P plus on M. And it's going to be defined by two short exact sequences of cohomology and differential geometry. Let's see if I can reconstruct this. So if I look at these things, I can think about a set of globally defined closed forms of P dimensions that are identified with closed forms that are integrally quantized, so that have a gauge transformation P. So this going to H check P plus 2. Go down to H P plus 2 of M D 0, and then 0. So there is this one sequence. So what is this thing? So this thing here is a set of global forms, global one forms AP with identification that omega P here. So that's one sequence that defines what a U1 gauge field is. Another sequence that's also important is I can take these gauge groups A from this holonomy A to be valued in some U1 in general, but not necessarily globally defined. So since the holonomy is in U1, so I take R H to be valued in H, let's say HP of some coefficient R mod Z. So H valued in R mod Z, and then the holonomy is in U1. There is another sequence which 0 going to H1 of the spacetime R mod Z into H check P plus 2. All such elements here that are in cohomology are going to be closed. Right? So then these will go to, it projects to a de Rham class, where this is not a de Rham, but omega P that are integrally quantized. Goes to 0. So this set here is the set of flux forms which are D of A of P, which are going to be valued in which are going to be some quantity which is in Z, which is in Z. These are a set of fluxes which are in Z. So when I think about a U1 gauge theory, I actually have these two sequences that defines for me the set of gauge invariant field configurations. And I can summarize this. There's a hexagon that people typically write to summarize what this looks like. So let me draw the hexagon, and please ask questions because this is going a little too fast. We can summarize this with the following hexagon, which is of differential cohomology. The PV goes to H check, which then goes to H P plus 2, H. I'm screwing up my dimensions. Sorry, I screwed up a bunch of dimensions. So this would be 1, it would be 1. This would be 1. This would be HP1 of V, which goes to 0. And then on this side, I have H1, HP, R mod Z, which goes here. This goes to closed P+1 forms, which are integrally quantized here. And there is a constraint that T's have to agree in their de Rham class, which is HP+1 in R. There's also a map that comes here, which is HP in R. So this sort of this diagram summarizes actually for us what are the set of gauge invariant field configurations. I'll get to that. And in general, if you observe this diagram, on top you have differential forms, and in the bottom you have cohomology groups. Okay, and the differential forms, there is a map here with a D, and then there's a map here which is a box D. Okay, so if you ever care to know what a U1 gauge field is, it's fully summarized by this diagram over here. And of course, this continues both sides because you have a de Rham here, so you can glue in another piece, and you can glue in another piece on that side. And this allows you now to think about the different parts that you want. So in particular of this question that we want to think about here is for the BF theory, we know that each one of these gauge fields are flat. So the curvature is 0. So that means that I'm looking at a set of gauge fields where this part vanish. Okay, so this part vanish, and then the gauge field themselves, when I started, they live here. This is where it seems to live. So actually, the set of flat connections that I care about here is going to be then summarized, where this is identified with H check by the sequence of omega p z into HP R mod z into HP+1. So this sequence tells you the sequence of flat U1 gauge fields, right? And this has a lot of structure to it, right? And in particular, if I started with the BF action, just from this thing already, classically, it tells me that I have to focus on, well, classically, because this is the first order, so the evaluating this path integral correspond to summing over flat connections of B and C. So naively, it seems this is trivial at the level of the action, but it is not, precisely because you have this whole data of things that are left over, from which you have to sum over. And because you have this whole thing, you can have non-trivial correlation sequence that survives. But not all of them survive, only the ones that are in the VN will survive. This was the question.
This AP that you're describing, is this a possible gauge field, or is it a field that has some action that and then is invariant under the?
So it's classifying this H check is a statement of the set of gauge invariant field configuration. So I have A, which has this gauge transformation, where it's identified with anything which is valued, which is integrally quantized, right? So naively, that would tell you that the gauge field should be H1 R mod Z, with R mod Z coefficient in H times, but not H1, H2, because I'm looking at two-form gauge field, H2 cohomology with R mod Z coefficients. But that's a little too fast, because the quantity that you should ask, as Chigger Simons taught us a long time ago, is you want to look at this this map, which acts on P cycles, which is given by the holonomy, and you want to understand what are all the possible configurations that exist. So it is not just this corner here in general for U1 gauge theory. There's a lot more data, and you can summarize it all with this diagram. Right? So if I have a U1 gauge field, the reason why U1 gauge field have a lot of structure that you cannot see at the differential level is precisely because of this diagram. And in our case, it collapses. H check just collapses here only because I'm looking at flat connections. But in a general gauge theory, I have a lot more things to keep track of. Right? So there is on top, you have a differential part, which is what we see when we write a Lagrangian, but then you have a cohomology part, which you don't see, and then you have to do work to keep track of that. Right? And the reason why the BF theory, if you look at it just naively as a differential form in the action, it looks like once you something of a flat connection, there is nothing left. But you have to account for the fact that there are elements that are valued in some cohomology group, and then you have to account for those in the sum, right? And that's what makes the theory non-trivial, and that's what also allows you to have non-trivial correlation functions. I apologize that this is so fast. This is a topic that deserves a whole other set of lectures. But if you're not familiar with it, I encourage you to read about it. I can send you a reference. Go ahead.
So